Cross-domain offline reinforcement learning promises to solve one of the biggest bottlenecks in AI, the need for massive amounts of environment interaction. By reusing datasets from a source domain, we can train policies for a target domain with dramatically less data. But there's a catch. When the dynamics shift between domains, blindly mixing datasets usually breaks the policy. Current methods try to fix this by measuring how similar a source transition is to a target transition, then reweighting the data based on that similarity. It sounds logical, but it's fundamentally flawed. And here's why. In reinforcement learning, the quality of a decision isn't determined by how similar the current state and action look to something you've seen before. It's determined by the long-term return that action will produce. Two transitions can look nearly identical in state and action space, but due to differences in mass, friction, or joint limits, one might lead to a stable jump while the other causes a catastrophic fall. If your value function learns from the wrong long-term return, your policy learns the wrong thing. This is exactly the problem that Target Bellman Backup, or TABB, solves. Instead of filtering data based on superficial transition similarity, TABB filters it based on Bellman target alignment. To understand why that matters, we have to look at how policy optimization actually works. Offline RL doesn't interact with the environment. It learns entirely from a fixed dataset by minimizing Bellman error. The Bellman backup decomposes the value of a state into the immediate reward, plus the discounted value of the next state. Policy improvement is entirely driven by these value estimates. If a source transition provides a Bellman target that's misaligned with the target domain's dynamics, it introduces bias into the value function. That bias propagates, corrupts the policy, and causes negative transfer. So the real measure of a source transition's usefulness isn't how similar it looks to a target transition. It's how consistent its Bellman backup is with the target domain's value function. TABB operationalizes this insight through a metric called Target Bellman Mismatch, or TBM. The goal is to quantify how much a source transition's Bellman target deviates from what it would be under target dynamics. We do this in a shared latent space. First, we encode states and state action pairs using separate neural networks. Then, we train a target domain predictor to estimate what the reward and next state latent representation would be if that same state action pair were executed under target dynamics. The TBM is simply the absolute difference between the source Bellman target and this target-aligned prediction. Crucially, we use an anchor value function that is trained exclusively on target domain data. This ensures the metric stays grounded in the target domain and doesn't get pulled by source dynamics. The training process is carefully staged to avoid contamination. In the first stage, we jointly train the encoders and the predictor on a mixture of source and target data. This is necessary because target datasets are usually tiny, and we need enough data to learn meaningful representations. But we know the predictor will still carry some source domain bias. So in the second stage, we freeze the encoders and refine the predictor using only target domain data. This isolates the target dynamics. Once the predictor is calibrated, we compute the TBM for every source transition. We convert these mismatches into transferability weights using an exponential decay function. Transitions with low TBM get high weights. Transitions with high TBM get down-weighted. Now, how does this actually update the policy? TABB integrates these weights directly into the critic update, following an implicit Q-learning framework. The critic learns from both target transitions and TBM-weighted source transitions, but it always uses the target-aligned Bellman target for its backups. The critic objective uses a Huber loss for robustness against outliers in the Bellman targets. Meanwhile, the value function is updated using an expectile regression loss, which handles the asymmetry between value estimation and policy extraction. The policy itself is extracted via advantage-weighted regression, strictly using target domain data. This is a critical design choice. Ablation studies show that using source data to train the actor directly causes severe performance degradation. The source actions might be optimal for source dynamics, but they're unsupported in the target domain. By restricting source data to critic supervision only, TABB extracts maximum value while completely avoiding negative transfer. There's also a strong theoretical guarantee backing this up. The paper proves that TBM acts as a proxy for the true target Bellman error. Under the assumption that the target domain predictor is accurate and the value function is Lipschitz continuous, TBM provides an upper bound on the bias introduced by source data. By downweighting high TBM transitions, TABB explicitly controls this bias. It's not just a heuristic, it's a mathematically grounded mechanism for stabilizing value estimation under distribution shift. The experimental results validate this approach across a wide range of challenging scenarios. TABB was tested on MuJoCo locomotion tasks like half-cheetah, hopper, walker-to-D, and ant, as well as adroit dexterous manipulation tasks like pen and door. The dynamics shifts included morphology changes, kinematic joint restrictions, and friction variations. In every case, TABB consistently outperformed existing methods like MOBODY, OTDF, and DARA. The gains were especially dramatic under severe dynamic shifts, or when source and target dataset qualities were highly heterogeneous. For example, when target data was expert level but source data was mediocre, transition similarity methods failed completely. While TABB still achieved strong performance by correctly identifying which source transitions actually contributed to accurate Bellman updates. Robustness tests across varying friction levels and dataset qualities further confirm that TABB scales gracefully with dynamics intensity. So what does this mean for the future of offline reinforcement learning? TABB represents a fundamental shift in how we think about cross-domain data reuse. We've spent years trying to match states, actions, and rewards. But policy learning is ultimately about maximizing long-term returns, and that's a Bellman problem. By aligning data selection with Bellman target consistency, TABB unlocks the true potential of cross-domain datasets without the pitfalls of negative transfer. It's a principled, theoretically sound, and empirically robust approach that pushes offline RL closer to real-world deployment. If you're working on data-efficient policy learning, domain adaptation, or offline reinforcement learning, this paper is a must-read. It redefines what it means for source data to be useful, and it gives us a clear path forward for scaling AI systems in complex, shifting environments.